Welcome to ThirdEye Labs, where we make the unseen seen. In Part 1, we learned the alphabet of math notation. Today, we learn to read full sentences. By the end, that terrifying line will read like plain English. A quick reminder from Part 1. The capital sigma is nothing but a loop that adds. We already speak this language. Now let us add the harder words. First, the curly d, the partial derivative. A normal derivative asks how the output changes as one input changes. The partial derivative asks the same question but with a rule. Wiggle just one input and hold all the others fixed. Think of baking a cake. To test how salt affects the taste, you freeze the amount of flour and sugar and only wiggle the salt. That is the only difference. Let us make it concrete. Take f of xy equals x squared plus 3xy plus y squared. To get the partial in x, we treat y as a frozen constant. The slope in x is 2x plus 3y. At the point 2, 1, that is 2 times 2 plus 3, which is 7. One number, that tells us how steep f is, in the x direction alone. Next, the upside-down triangle, called nabla, the gradient. This looks scary, but it is not new. It is simply all the partial derivatives gathered into one vector. The gradient points in the direction of steepest increase. Straight uphill. Imagine standing on a foggy mountain. You feel around with your feet to find the steepest upward slope. That direction is your gradient. Now the fancy-looking e with square brackets, the expectation. It sounds advanced, but it is just a weighted average. Multiply each outcome by how likely it is and add them up. It is like planning a commute. If a 15-minute drive happens 80% of the time and a 45-minute delay happens 20% of the time, your realistic expectation is 21 minutes. For this loaded die that favors 6, the expectation leans high to 4.5. That is all expectation means. Here is a beautiful one. We know the sum, sigma, adds up a list of bars, but what if we make those bars thinner, and thinner, and thinner? As the steps shrink towards 0, the staircase becomes a smooth area. The sum becomes an integral. It is the very same idea, adding up slices, just infinitely fine. Just like a digital water meter continuously measuring flow instead of counting buckets one by one. When a paper takes an expectation over a continuous world, this stretched out S is the sum it means. Next, the double bars around a vector, the norm. It just means size, the length of the vector. The L2 norm is the straight line length, like a drone flying directly to a target. The L1 norm adds the absolute values, like a taxi driving along city blocks. Norms are how a paper measures distance and the size of a gradient. Here is the single most common line in any machine learning paper. Theta star equals arg min of the loss. The trick is the difference between min and arg min. Min is the smallest value the curve reaches. Arg min is where it happens, which input produced it. Think of a household thermostat. The minimum is the low electricity bill, but the arg min is the actual 70-degree setting you program on the dial. So this line just says, the parameters that make the loss smallest. That is the entire goal of training. Now watch every idea so far come together. This bowl is the loss. Low is good, high is bad. Our model starts somewhere up the side with a bad guess. The gradient nabla points straight uphill, so to get better we step the opposite way. The negative gradient, downhill, we take that step again and again. Each one lowers the loss. And that is the entire secret of how a neural network learns. Arg min is the goal, the gradient is the compass. Every step is training. First, the operator at the end of almost every classifier, Softmax. Do not let the formula scare you. Here is what it actually does. On the left, the network's raw scores for cat, dog, and bird. Just numbers hard to read. Softmax turns them into clean probabilities on the right that are all positive and add up to 100%. Just like a sports bookie taking arbitrary team scores and turning them into clean betting odds. The biggest score becomes the biggest probability. That is the whole job. Two more operators you will see constantly, and both are simple shapes. Sigma, the sigmoid, gently squashes any number into the range 0 to 1, like a smooth dimmer switch. And ReLU is even simpler. It keeps positive numbers as they are, and flattens every negative to 0, acting like a surge protector. That little bend is what lets a network learn curves instead of straight lines. Information theory sounds heavy, but it starts with one cozy idea: surprise. A fair coin 50-50 is maximally surprising. You can never guess the result. A rigged coin that lands heads 99% of the time is barely surprising at all. Entropy, written capital H, is simply the average surprise. It is like smartphone autocomplete. Typing good morning has low entropy because it is expected, but typing good tractor is highly surprising. High for the fair coin, low for the rigged one. From that one idea, a few symbols follow. Capital H of X is entropy, the average surprise we just felt. Capital H of P and Q is cross-entropy, and this is the actual loss used to train classifiers. It measures how surprised your model is by the true answers. DKL is the KL divergence, how far your model's guesses are from the truth. And I of X and Y is mutual information, how much knowing one thing tells you about another. If knowing the weather tells you a lot about umbrella sales, those two share high mutual information. Now a beat almost no one explains, and it unlocks so much. The tiny marks on top of a letter completely change its meaning. A hat means an estimate, a prediction. Y hat is what the model thinks, like a weather forecast. A bar means an average. X bar is the mean of your data. A tilde means a noisy or modified version. And a star means optimal, the flawless true value. Learn these 4 marks, and whole sentences of a paper suddenly snap into focus. Put 2 together. Theta hat is approximately theta star reads as, our estimate of the parameters is close to the optimal ones. 4 little marks, and you can state the goal of an entire training run. Linear algebra is the whole of Season 1, so just a taste here. When a matrix transforms space, most arrows get rotated and stretched. But one special direction only stretches, it never turns. Like rolling out pizza dough, most parts squish and twist, but the center line just expands straight outward. That direction is called an eigenvector, and the amount it stretches is lambda. A v equals lambda v. We will spend a whole episode on this soon. 3 more you will spot. A to the -1 is the inverse, the matrix that undoes A. Double bars with an F, the Frobenius norm, is just the size of an entire matrix. And rank counts how many truly independent directions a matrix has. Theory sections lean on sets. A picture makes them obvious. 2 groups O and B. The union, the cup, is everything in O or B together. The intersection, the cap, is only the overlap, the part in both. The rounded subset sign means a sits entirely inside B, and bars around a set just mean its size. The set A, B, C has size 3. And 4 bits of logic glue. There exists with an exclamation means exactly 1. ST means such that. The 3 dots mean therefore. And the solid black square at the end of an argument means the proof is done, what mathematicians call QED. Papers also compress plain English. The 3 you must know. WRT means with respect to, as in the gradient with respect to theta. ST means such that, or subject to, used for a constraint. And IID, everywhere in theory, means the data points are independent and identically distributed, drawn the same way and not affecting each other. Finally, 3 arrow shapes people mix up. Colon equals means is defined as, the plain arrow describes types, F goes from set X to set Y. The bar arrow describes the rule itself. This input is sent to that output. Types versus rule. Once you see it, you cannot unsee it. One more from the abstracts. Big O notation. It does not measure exact time. It measures how the cost grows as the input gets bigger. Order n is a straight line. Order n log n bends gently upward. Order n squared explodes. When a paper turns n squared into n log n, this gap is the whole prize. Now we read the whole sentence. Here is that cold open line again. It used to be a wall. Watch it dissolve. Arg Min means find the settings. 1 over n, sum, means that on average. The log p term measures how surprised the model was. Put it together, and the line simply says, find the settings that, on average, make the model least surprised by the data. That is it. The terrifying formula was a plain sentence all along. Now here is the payoff. Let me show you 3 famous research papers. Every single symbol in their key equations was covered in this video. You can read them right now. Paper 1, Generative Adversarial Nets by Goodfellow, published in 2014. 9 pages. Change to I forever. The entire paper is built around this one line. Min G, max D, 2 players. A generator G trying to fake data, and a discriminator D trying to catch it. The E brackets are the expectations we just learned. Log D of X is how confident the detector is on real data. Log 1 minus D of G of Z is how badly the generator is fooling it. That is the whole idea. A game, written as one line of math. Paper 2. Attention is All You Need by Vaswani and team, 2017. This paper invented the transformer, the architecture behind GPT, Gemini, and every large language model. Its core formula is this. Q, K, and V are 3 matrices, query, key, and value. QK transpose is just a dot product, computing a similarity score. We divide by the square root of dk to keep gradients stable. Exactly the norm idea we covered. Then Softmax, which we just decoded, turns those scores into weights that sum to 1. Multiply by V, and you get the attended output. Every piece of this formula is something you now know. Paper 3. Atom by Kingma and Ba, also 2014. This is the optimizer that trains almost every neural network today. GT is the gradient, nabla of the loss, the compass we used in gradient descent. MT is a running mean of past gradients. VT tracks the squared gradients, the variance. The hats on M hat and V hat mean bias-corrected estimates, exactly the hat notation we decoded. And the final line is the weight update. Move theta in the direction of negative M hat, scaled by the adaptive rate. Arg Min is still the goal. Atom is just a smarter way to walk toward it. All 3 papers are free to read online, links are in the description. And here is a question for you. Which of these papers do you want me to walk through line by line in a full dedicated video? Comment GAN, attention, or Atom below. The one with the most comments gets made first. Every vote actually decides the next video. Let us recap the decoder ring. The partial D means wiggle one input and freeze the rest. Nabla is all the slopes in one vector. The integral is a sum gone smooth. Arg Min is where the minimum lives, the goal of training. Softmax and ReLU are the operators inside a network. Entropy, cross-entropy, and KL divergence give us our losses. And the little marks on top. Hat is an estimate, bar is a mean, tilde is noisy, star is optimal. Stack all of these, and there is almost no symbol in a modern paper you cannot now read. Thanks for watching and keep exploring. Next time, we begin Season 1, the language of AI itself, linear algebra, where a matrix becomes a transformation of space. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.